Welcome to Patterns of Atrocity, the video series where we talk about the interdisciplinary fields of computer science, sociology, and history to model genocide and learn what can be learned about preventing genocide to shape a future free from atrocity. In the last episode, we analyzed an essay that came to a conclusion using agent-based modeling that high levels of societal levels of restraint were preventative of genocide. In today's episode, we're going to try and recreate this experiment using our own agent-based models and try and visualize what is happening. For this project, I'm going to be taking code from a YouTube channel called Primer, whose videos circulate around simulating agent-based modeling, and whose code is open source and free to use. So the first step is to look at this GitHub and download the necessary applications we'll need to run these models. This code uses a combination of Unity and Blender, which are applications designed around rendering animations. Luckily, I've used them before, but I still anticipated this being a struggle to actually get this code to run. After carefully reading through the GitHub and downloading the necessary tools, it was time to load in Primer's objects so that we could start messing around with them. And after finally loading everything in, everything's pink, so I obviously did something wrong. Luckily, I was able to find a YouTube video detailing the exact nature of this bug, and it just required me to relaunch the applications. And suddenly, everything was going smoothly. In all honesty, a lot faster than I expected. The Primer code, handily enough, came with a couple of demonstrating scenes, but it uses these little blob characters to represent agents. My first step was to fill a scene with 100 agents and see if I could do that, and that went smoothly. Our next step was to split the agents into two different groups. We'd have a blue group and a red group, each with representing 50% of the population at the start of the simulation. So as we can see, when we generate agents into our starting scene, there's an equal chance that each agent will be assigned to the red group or to the blue group. Our next step was to encode the agents with the parameter described in the paper. So an ideology, influence, susceptibility, and threshold to act. If you don't know what those means, go back and check out my previous video. Our next step was to randomly initialize these variables from a range of 0 to 1, 1 being a higher attribute of this trait, as well to allow the agents to move over each generation, which will be shown in the following simulation. The idea here is that each agent will move over a generation and interact with nearby agents to change its susceptibility or threshold to act over time. Our next step is to encode the logic for how these agents will interact with each other. If you haven't seen my last video, I'll go over it briefly here. Basically, each agent will move over the course of each generation and then identify the most influential agent with the same identity in its radius of sight. That agent will then update its ideology based on the agent that it identifies to be the most influential. At the end of each generation, if any agent's ideology is greater than its own threshold to act, it'll kill all other agents of opposite type within its radius of sight. As you can see in my first simulation, I had the radius of sight be the entire scene, so the blue group killed the entire red group within one generation, so that had to be updated to lower the radius of sight. And then the last and final piece of the interactions was that each agent has a chance of reproducing at the end of each generation. As you can see, we're corroborating the paper here in its experiment 1, that with these settings, over the course of many generations, one group always dominates over the other group. Our next step was to do the paper's second experiment, which is instead of codifying a random range for each agent's threshold to act, have the threshold to act be defined at a society level, such that every agent has the same threshold to act. And we can see already with these settings, even though the average is still the same, the generations are living for a lot longer. However, even here, one group seems to be dominating the other group as we continue to go on for many generations. And I realized this had to do with the way I was setting the initial settings. In the paper, they randomized these settings from 0 to 1, but using a uniform distribution. I just randomly picked values from 0 to 1, meaning that our variance for each agent was a lot greater than that defined in the paper. So I had to update these settings and rerun the model for one last time. And as this video plays out in 5 times speed, we'll see that the generations stabilize and no group ends up dominating the other, even over many, many generations. In my last video, I talked a lot more about what these results could actually mean for genocidal research. And while I'm happy here that we were able to corroborate the results, and I think this visualization of this paper is useful for understanding what's going on, I think it's worth talking about some of the drawbacks of using agent-based modeling here. Obviously, this model is a vast oversimplification of the real world, so it's important to be careful about any conclusions we might make from this model. The key and the next step for this model would be to try and verify its results using real-world data. And I want to emphasize that I chose one of the simplest models for this start of the video series. There's research that builds off this model and builds up more and more interesting results as we make more and more complicated models. But even so, even from this possibly the most simple model we can make, we can still come to the conclusion that societal levels of restraint are useful in preventing genocide. And I think that's a profound finding. I hope you were able to learn something from this video series, or at least found it interesting. The next steps here, if I were to continue this, would be to look into more papers and try and build up this model to be more complicated, more sophisticated, and a better example of the real world. That being said, thanks for watching.